Good day, learners. Welcome to our mathematics lesson. My name is Nagile Ndlovu. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Yes, thank you, boys and girls, for attending. Welcome to our today's session. We're going to be focusing on trigonometry, and in particular, we'll be looking at trig identities. That is, how do we derive our trig identities and then apply them to solve some trig expressions and eventually use them to solve some equations. Yes, we are saying by the end of this lesson, you should be able to draw a right angle triangle in the first quadrant and use it to derive your trig ratios. 2, you should be able to derive the identities cos squared alpha plus sine squared alpha equals to 1 or identical to 1, and then tan alpha is equals to sine alpha over cos alpha, right? Those two are identities. I specifically used alpha there. You can use any other variable. It could be cos squared x plus sine squared x is equals to 1. Any variable that you use for the angle there will still hold. Then 3, we want to use the identities cos squared alpha plus sine squared alpha equals to 1 and tan alpha equals to sine alpha divided by cos alpha to simplify trig expressions or trigonometric expressions. Then in number 4, we should also be able to prove trigonometric identities by selecting one side and simplifying to give the same result as the other side. You will realize that in number 4 there, which identities are we proving? There are quite a number of identities in mathematics that one can prove. So you shall see as we continue, it's not only the 2 that you see on the screen there, which is cos squared theta plus sine squared theta equals to 1. Sometimes they use theta, or tan theta equals to sine theta divided by cos theta, and then those 2 are also equal. Right, so these are not the only 2 identities that we have in trigonometry or in mathematics in general. There are quite a number of trig identities. But but these ones are the ones that we are going to focus on in today's session. Right, if you look at our pre-knowledge by now, I'm expecting you to be conversant with the Cartesian plane, the radius of a circle, then the right angle triangles and acute angles. You should be in a position to apply Pythagoras' theorem. Then you should be in a position to identify trig ratios for sine, cosine, and tangent. You should also be able to factorize by using common factors, and then simplification of fractions as well as substitution. We are going to define some of these terms just to remind you of some concepts thereof. Right, we are saying, what is trigonometry in general? It is that branch of mathematics which deals with relations between sides and angles of a given triangle and with the relevant functions of any angles. When you say it is a branch of mathematics, we know mathematics has to deal with mainly the 4 basic operations: addition, subtraction, multiplication, and division. So it's that specific branch of maths that seeks to find the relationship that exists between the sides of a given triangle and its relevant angles. A radius of a circle is a straight line drawn from the center of the circle to any point on the circumference of the circle. Right. A right angle triangle is a triangle which contains a 90-degree angle. And you'll realize that this 90-degree angle is going to be the biggest of all 3. The moment one corner becomes 90, the other 2 angles will become complementary angles, meaning they must build the other 90 so that the overall result, some of the interior angles of that triangle, will give us 180 degrees. Then trigonometric identities are the equalities that involve trigonometric functions and holds true for all values of the variable given in the equation for which both sides are defined, meaning there are now no zero denominators, meaning in those questions that have quotients, you must check if the denominators are not zero. Otherwise, the whole fraction will be invalid. It won't be defined whenever the denominator is zero. So there is a slight difference between identities and equations. We shall see later on how equations differ from identities. Why sometimes we write identities with an equal sign instead with an identity symbol. Okay. Then an acute angle is an angle which is greater than 0 degrees but less than 90 degrees. Otherwise, 0 degrees and 90 degrees are special angles. Then trigonometric substitution is the replacement of a trigonometric function for another equivalent expression. Okay, right. We are going to begin our lesson by referring to the sketch that you see. In this sketch, we have what we call a terminal arm. Our terminal arm, I will call it OP. This is our terminal arm. It starts from the origin. It extends to the circumference of the circle at point P. That's why we are naming it as our radius R, which is a distance from the center of the circle to the circumference of the circle. It's a straight line. Now, we are going to form a right angle triangle by dropping a perpendicular line from point P towards the x-axis. Then we'll form a 90-degree angle here. Every time you draw this triangle, you'll always have what we call a terminal arm. This is your terminal arm, of your angle. So our terminal arm here, we are going to call it a OP, and its name in this case is going to be the radius R. So as you drop a perpendicular from P to this point that I will call maybe Q, a 90-degree angle is formed. It means our triangle OPQ is a right-angled triangle. So our OPQ is a right-angled triangle. OPQ triangle, OPQ is a right-angled triangle. It's a right-angled triangle because it contains a 90-degree angle. So the distance PQ is parallel to the y-axis. We are going to name it as the y side. Then the distance OQ is running on the x-axis. We are going to name it x. Now we are then going to define, going back to what we did in grade 10, to say how do we define the three trig ratios or trigonometrical ratios. Remember, a ratio is a fraction. We are comparing quantities. So in this case, we want to find the relationship that exists between y and r, between x and r, and between y and x. Once we form those ratios, they will have specific names. These names are sine, cosine, and tangent, depending on the particular ratio that we would have formed. Why do we call them ratios? Because their answers are in fractional form, which can also be written in ratio form. When you say y over r, it's the same as saying y is to r. It's a ratio. Out of y, r items, I'm taking y. So my ratio is y is to r. The other ratio is x is to r. The other ratio is y is to x. All these are ratios. So the functions that we form, therefore, are called trigonometric ratios. So you can only form them by using SOHCAHTOA. SOHCAHTOA with an A at the end. That's the word that we use to identify our trig ratios. So our first ratio is sine. So how do we define sine? This is our sine. Sine is equals to, sine we use these with reference to a particular angle. When we are saying opposite side and hypotenuse side, our hypotenuse side will always be the longest side in our right angle triangle. So in this case, our longest side is our R, and our other two sides are X and Y. These will either become opposite and adjacent depending on our point of reference. So what does this mean? It means you first have to identify your point of reference, which in this case is angle theta. That is the angle of inclination of our line OP. We rotated from the 0 degrees up until we rested on OP, at which time it became our terminal arm. So OP being the terminal arm, it means we have to rotate through a certain amount of 10, which is what we have defined here as our theta. So our theta is going to be our angle of reference. So when I'm positioned at theta, Y becomes the opposite side and X becomes the adjacent side. Otherwise, our R will be, our radius is a distance from the center to the circumference of our circle, which is at point P. So by definition, how do we define sine? Our sine is equals to the opposite side divided by the the hypotenuse side. Opposite side divided by the hypotenuse side. So in this case, when you check your diagram, your opposite side opposite the angle is Y. So it's going to be Y divided by our hypotenuse side is our R. Therefore, our ratio sine theta is given by Y divided by R. That is our ratio for sine. The same applies to cosine. How do we define cosine? Cosine is going to be adjacent side divided by the same hypotenuse side. So the cos of theta is equals to adjacent side. You have to identify your adjacent side, divide by the hypotenuse side according to our SOHCAHTOA there. Then when we go back to the sketch, our adjacent side is a side that is placed closer to the angle theta. It's just positioned to theta, so it's X. So it's going to be X divided by our R. So our cos theta will then become X divided by R. Then final, our tangent of theta as our third ratio. We'll then say, how do we define tangent from that word SOHCAHTOA? We see an O and an A. Our O is the opposite side still. Otherwise, our A is the adjacent side. We have identified those sides. According to this sketch, this is our opposite side. This is our adjacent side. And then this is our hypotenuse side. That's how we label our diagram based on the angle of reference. Our angle of reference is theta, meaning when I'm at theta, as I look across in front of me, I see Y, that's my opposite side. Next to theta, I see X. Otherwise, I also see R, but R has got a special name. Its name is the hypotenuse side. Therefore, we are going to identify those sides in this manner to say with reference to angle theta, our Y is the opposite side, is directly opposite angle theta. Otherwise, our X is very close to theta, is called an adjacent side. Then our longest side in that right angle triangle will then become our hypotenuse side. So by definition, sine is the ratio which compares the vertical distance, which is the Y side, divided by the longest side in that right angle triangle, which is your hypotenuse side. The hypotenuse side is always placed directly across the 90-degree angle. Since 90 degrees, the longest side, longest angle in the triangle, therefore our OP will become our longest side in that particular triangle. And that longest side was given a special name, is the hypotenuse side. Then we move on. Now that we have established our ratios, as in saying our sine theta is equals to Y divided by R, and then our cos theta is equals to X divided by R, adjacent over hypotenuse. What are we then saying? We are going to derive today our identity cos squared theta plus sine squared theta is identical to 1. In other words, when you say cos squared theta, cos squared an angle added to sine squared of the same angle, the answer is always A1. Why is the answer always A1? Right. We are going to have a look at how we derive this so-called identity. We normally call this one the square identity. There are reasons why we call it a square identity. Otherwise, I'm going to move on with you and show you how we derive this identity cos squared theta plus sine squared theta is equals to 1. Right. When you look at this ratio that we have established just now, sine theta equals y over r. How do I derive cos squared theta plus sine squared theta is always equals to 1? I'm going to square both sides of sine theta. If I say sine squared theta, what have I done? I have squared the number that is on the left hand side, because that sine of theta will eventually become a number, right? Since it's an equation, what I do on the left hand side should be done on the right hand side as well. So this is going to be y squared divided by r squared. I'll leave this equation and move on to the other side. I'll do likewise. I'm going to square cos and get cos squared theta. And you must be careful when you square these functions in mathematics. We don't square at the end or put the square at the end, because at the end of the day you are now squaring the angle. You are not squaring the function itself. You have to square the value of the function. Cos 20 degrees is a number, then you square it. So to avoid squaring the angle, you'll have to put the square number between s and your theta as a small number. Cos squared theta is written like this, not to write it as cos theta squared. You must avoid writing it like that. Otherwise, you'll end up squaring the angle instead of squaring the overall result. So you need to know how to represent your trig ratios in square form, cube form, and so on. So since I have squared the left-hand side, I'm also going to square the right-hand side on this equation, which gives me r squared, x squared divided by r squared. Right, according to this identity, we are supposed to add these two and see what happens. I'm going to add the two. How do I add the two? I will say cos squared theta added to sine squared theta. I'll take my result of squaring both. Our cos squared theta is the same as x squared over r squared added to y squared over r squared again. What do we notice here? Look at that sine cos squared theta plus sine squared theta that I've written here in red. We have x squared plus y squared over r squared over r squared. What do we notice there? Yes, we notice that there is a common denominator, which is r squared. Then we have x squared plus y squared equals to cos squared theta plus sine squared theta equals to x squared plus y squared, both over the same common denominator, r squared. But I remember seeing x, y, and r. Let's go back. There is our x, y, and r. These are the three sides of our right angle triangle. And these three satisfy Pythagoras' theorem. But according to Pythagoras' theorem, if I may extract that triangle out, this is our 90, this is our r, this is our x, this is our y. And we are saying, according to Pythagoras' theorem, there is a relationship amongst these three. Pythagoras' theorem. What do we know about Pythagoras' theorem? It says the longest side squared in a right angle triangle is equals to the sum of the squares of the other two sides. That's what Pythagoras theorem says. It only applies in a right-angled triangle. The longest side in a right-angled triangle is equals to the sum of the squares of the other two sides. So what does this mean? It means r squared is x squared plus y squared, meaning where I see x squared plus y squared, I can replace and put r squared. Therefore, what are we saying here? We are saying cos squared theta added to sine squared theta is equals to, I'm going to replace my x squared plus y squared using r squared because I have established that relationship amongst those three in a right-angled triangle, wherein Pythagoras theorem applies. So this is now going to be r squared divided by r squared. R squared divided by r squared is equals to 1. A number divided by itself is 1. Therefore, in conclusion, our cos squared theta added to sine squared theta is always identical to 1. It is always identical to 1. We were not specific as to what angle we are working with here. We chose a particular angle theta. Theta can be half degrees, theta can be 30 degrees, theta can be 0.8 degrees, theta can be 100 degrees, theta can be any angle on this diagram. Sometimes theta is also found in these other quadrants. So it means what we have derived here is an identity. In other words, if we were to use any angle, this will hold. If we were to say, for example, you say sine squared 30 degrees, what is important is to maintain the same angle, plus cos squared 30 degrees, the answer will always be 1. Even if you change that angle and put any other angle, the answer will always be 1. If you say sine squared 0.5 degrees added to cos squared, you can punch this on your calculator right now, squared, the answer again will come back to 1. So what does this mean? It means this is a special equation. This special equation is called an identity, and it uses a special symbol. That special symbol is an identical symbol. So all identities use this identical symbol. The same identical symbol. The same symbol, we use it when we are comparing triangles to say the triangles are congruent. It indirectly means they are identical to each other. So here, when we use this symbol in our identities, it means the left-hand side is identical to the right-hand side. But then the question is, what then is an identity? Based on what we have done here, we realize that cos squared theta plus sine squared theta is identical to 1. In other words, this is another way of writing 1 in trigonometry. Our 1 as a numerical value is just that one normal 1 we know as in counting 1, 2, 3. In trigonometry, our 1 comes in function form, which is cos squared theta plus sine squared theta. Never mind the size of the angle. As long as that angle is maintained, the cos squared theta plus the sine squared theta will always yield a 1. So this is our 1 in trigonometry. That cos squared theta plus sine squared theta is equivalent. It is equal in value to 1 upon substituting for the value of theta. Theta can be any angle. Right. So what we sit with here is called an identity. What then is an identity? All identities are equations, but not all equations are identities. An identity is a special equation in which all values for the variable make both sides balance for the defined values of the identity. So whatever statement you are given, if you are told that this is an identity, then it implies whatever value you substitute, you will always get the same answer as the left-hand side or right-hand side, depending on which side you substituted first. So an identity is a special equation in mathematics in which all values make the statement true. It means it is an identity. We also have identities in algebra, but for today, we're focusing on identities in trigonometry. So the identity that we have so far derived, cos squared theta plus sine squared theta is identical to 1, is called a square identity. We call this a square identity. We'll explain why we call it a square identity. Okay? But what we are emphasizing here is that all identities are equations, but not all equations are identities. What does this mean? It means in an identity, any value for the defined part of the identity will make the statement true. It doesn't matter which angle you use, but the statement will be true, especially in the region where the functions are defined, because there are some that are not defined in specific positions. But for all those that are defined in a given domain, then it will imply that any angle that you use, the two sides will always balance. Otherwise, why are not all equations identities? For example, a quadratic equation has only two solutions and not more than two. It cannot be satisfied by any other value except those two specific values if you were to solve it. That's why we are saying all identities are equations, but not all equations are identities. There are some equations that don't qualify to be identities. There are some equations that qualify to be identities, like this identity that we have just derived. This identity qualifies to be called an identity because of its special property. What is this special property? Its special property is that it balances for all values of x where it is defined. Now we call this type of an identity a square identity. We call this a square identity. Cos squared theta plus sine squared theta is identical to 1. The same identity can be written as cos squared theta plus sine squared theta is equals to 1. It can be written as an equation because all identities are equations, but not all equations are identities. Right. So what are we then saying? The same identity can be written as cos squared theta equals 1 minus sine squared theta. What have we done here? We have made cos squared theta the subject of the formula. Or sine squared theta is equals to 1 minus cos squared theta. This time around, we have written the identity in terms of our sine squared, making sine squared the subject of the formula. You're basically solving for cos squared theta, making cos squared theta stand alone. Then you transpose your plus sine squared theta to the other side. It will become a negative sine squared theta. Right. And then the same applies to sine squared theta. We are going to transpose our cos squared theta to the other side. It was a plus. It will now become a negative cos squared theta. So this identity can be written in 3 different ways. We call it a square identity. We now want to explain why we call it a square identity. Most people will refer to this one as a square identity. Do we possibly have a reason why we call it a square identity? If I may ask that question, do we perhaps have a reason why we call this identity a square identity? Yes, definitely yes. Because what I see here are square numbers. Cos squared theta is a square number. Because already you are saying cos squared. You are squaring that number is a square number. Sin squared is also a square number. 1 from our normal numbers, 1 is also a square number. A square number, remember, are numbers like 1, 4, 9, 16, 25, and so on. Those are square numbers because they can be written in squared form. 1 squared is still a 1, so it's a square number. 2 squared is a 4, so 4 is a square number. We square 2 to get a 4. So this identity has a special name. We call it a square identity because we are seeing on both left-hand side and right-hand side is made up of square numbers. The moment you say cos squared, it means it's a square number. Real via bus, it means it's a bus. Cos squared theta, it means it's a square number. Sin squared theta, it means it's a square number. Otherwise, 1 squared is 1, so 1 is also a square number. Therefore, these three represent the same thing. Cos squared theta equals 1 minus sin squared theta. Then sin squared theta equals 1 minus cos squared theta. We will need these later on for substitution to say where I see 1 minus sin squared theta, I can as well write cos squared theta. That's how you play around with them. Where I see sin squared theta, I can replace and put 1 minus cos squared theta, depending on the situation, depending on the simplification that one has to do. Furthermore, you may not really understand what I'm saying here because it's algebraic. If I were to say to you 3 over 10 added to 7 over 10, these two build a 10 over 10, which is equals to a 1. It's the same concept that I'm explaining here. Because these are fractions. There are no whole numbers that add up to 1. So the fact that I'm adding 2 squared numbers and the result is a 1, it means those numbers are fractional numbers. Otherwise, if they are not fractional numbers, the result will never be 1. So that's why I'm showing you this example of 3 over 10 added to 7 over 10. It gives us a 1. It's a whole. Then what if I wanted to write make 3 over 10 the subject of the formula? What does it mean? It means 3 over 10 is the same as 1 minus 7 over 10. Where I see 3 over 10, I can put 7 over 10. Where I see 7 over 10, I'm making 7 over 10 the subject of the formula. I can have 1 minus 3 over 10. They are equal in value. The same applies to the square identity. It can be written the same thing in 3 different ways. By transposing 1 or using the additive inverse, you subtract a sine squared from the left-hand side, subtract a sine squared from the right-hand side. You will get the middle one. Then by subtracting the cos squared from one side and subtracting it from the other side, those are additive inverses. Then you will get the second one. Otherwise, these 3 are 1. It depends on which one you want to make the subject of the formula. Hence, I'm emphasizing, you will never add 2 numbers in math that are squared and get a 1 unless and until those numbers are fractional. It's impossible. Because already the moment you say 5 squared plus 7 squared is way above 1, it will never yield a 1. This can only work if those numbers are fractions. So what does this imply? It implies cos theta is going to be a fraction. You square it, it will remain a proper fraction. Then sin theta will also be another proper fraction. You square it, it remains a proper fraction. You add those 2, they will give you your 1. This is a very, very important identity in trigonometry, what we call a square identity. And it has three variations. You can either write it as sine cos squared theta plus sine squared theta is equivalent to 1, or cos squared theta equals 1 minus sine squared theta is still fine, or sine squared theta equals 1 minus cos squared theta. Otherwise, we're moving on. Now, having said that, we are going to move on to the next identity that needs to be proven. But let's remember what we said earlier on. We agreed earlier on that our trig ratios are sine theta is equals to y divided by r, if you still remember. And then our cos theta is equals to x divided by r. Otherwise, our tan theta is always equals to y over x. That is the opposite side divided by the adjacent side, with reference to the sketch that we saw earlier on. Now, there is this other identity that we would want to derive. When you are deriving an identity or a formula, you are finding where it came from. How did they know that tan theta can split down to sine theta divided by cos theta? We will only get the answer upon referring to our trig ratios. So I'm going to divide here sine by cosine. If I say, what is sine theta divided by cosine of theta? Just for argument's sake, sine theta divided by cosine of theta. The angle is the same. Then this implies I'm talking about y over r, which is for sine. I will deliberately say divide by x over r, which is cosine. It's the same because I'm replacing. It's only that I didn't want to divide and put fraction over fraction. I've chosen to use a symbol instead of a division line. So we have sine theta is y over r divided by cos theta x over r, still the same. Now let's go back and use our multiplicative inverse. When you are using the multiplicative inverse, it means you are going to tip and times here. When you are dividing by a particular fraction, it's the same as multiplying by its reciprocal, which is its inverse. So in this case, I'm going to say y over r, you maintain your first fraction, then you multiply, you convert your division to a multiplication, then you invert the second fraction and then simplify. What do you notice? Yes, these can cross divide. R into itself 1, r into the other r is 1. R is gone. So what's left now is sine theta divided by cos theta is equals to y divided by x. Then we stop there. I remember seeing y over x as I was defining my functions. I remember seeing y over x in that diagram is equivalent to the ratio tan. Tan of theta is opposite side divided by the adjacent side, which is y over x. But surprisingly here, when I divide sine by cosine, the result is the same, y over x, which is what I saw earlier on. What does this imply? It implies I have established another identity. These things are identical, meaning in mathematics, if I see tan theta, it's the same as saying sine of theta divided by cosine of theta. They are identical. And remember, we did not become particular here or chose particular values of theta. Our theta is any angle. So meaning any angle makes this identity true. But you must be very careful here because there is a quotient today. There is a quotient, meaning some angles may fail us. We have drawn these graphs before. We know there is a problem with 90 degrees. Cosine of 90 degrees will always yield a 0. You can punch that on your calculator right now. Cosine of 90 degrees will always yield a 0. And its multiples in odd manner What do I mean by in odd manner? If you multiply 90 by 1, you get a 90. You can't press cos 90 and keep it in the denominator because cos 90 is 0. When you move on to an odd number, you take a 3. You multiply 90 by 3, you get 270. It's also going to yield a 0. So this identity does not work for certain values of theta, which is those values of theta that are using 90 degrees in odd integers. Odd integers meaning you are using 1, you are using 3, multiplying 90 by 3, you are using 5, you are using 7. It will work for 2. It will work for 4. It will work for 6. But the moment you use 90 by 1 in the denominator, it won't work. The moment you use 90 by 3, it won't work. That's why the qualification here is for k an odd number. It will never work. So this is a restricted denominator. There will come a time when the denominators are zeros. We don't want 0 denominators. Otherwise, this fraction won't be defined. But nonetheless, the function will be defined for all values of theta except the multiples of 90 that use odd integers. So we have established yet another identity. Tan theta equals to sine theta divided by cosine theta. It's a very special identity also. It's called a quotient identity because there is an element of division. This is your divisor, your dividend, and tan theta is your quotient. Hence, we call it a quotient. Remember, we talk of a quotient in division. When you say 3 divided by 2, your 3 is your dividend, your 2 is a divisor. Otherwise, the result is a quotient and the remainder. Okay, that's why we call this one a quotient. But of emphasis here, of interest here is how do we derive or how do we establish, how do we convince the next person that tan theta is the same as sine theta divided by cos theta. You always go back to your definition of your basic trig ratios, sine theta, cos theta, and tan theta. By definition, our sine theta is y over r, our cos theta is x over r, and our tan theta is y over x. When you divide these two other functions, sine divided by cosine, it yields y over x, which is the same as tan. That's where those two identities came from. Otherwise, we have shown each other how you can derive these identities. We now want to move on and have a look at how we apply those two to answer some questions. Our first question for the day says, that is example number 1. Simplify the expression as far as possible. We are given sine x divided by cos x multiplied by tan x. This is where you apply your identities. You need to replace some functions here and write them using their equivalence. So we can already see here we have sine x divided by cos x times tan x. This question can be answered in 2 ways. We are going to have a look at both ways. Right, let's have a look at the first question. The first question says sine x divided by cos x times tan x. You will remember tan x can be rewritten as sine x over cos x. So we're going to say sine x divided by cos x multiplied by, you stop there because you are simplifying. Is there an identity that I can use here? Is there an identity that I know can assist me here? Yes, don't forget your tan theta. In this case, is tan x equals to sine x. It doesn't matter the variable, divided by cos x. as long as you maintain the same variable. So it means where I see tan, I can replace and say sine x divided by cos x. That's how you play around with those identities in simplification. Now that we have broken down tan and written it in terms of sine and cosine, you will realize that these are fractions. You can cross divide. Cos into itself is a 1. So we have eliminated cosine in the picture. We are left with sine x in the numerator divided by another sine x in the denominator. Then a sine dividing itself, sine into sine x is like a number dividing itself. The answer is a 1. Sine x can only go into itself once. Okay. Alternatively, one learner could have said, what if I say, this is your alternative approach, alternative method or simplification. Right. You could have said, oh, I'm noticing something here. I have sine x in the numerator divided by cos x there, and then this is multiplied by 1 over tan x. Must be careful. That tan is a denominator. It's not just tan. That's why it says sine x over or divided by tan x. So this gives us another tan. So we're going to have tan from sine over cosine is always tan x over 1 multiplied by 1 over tan x. It's up to you here to decide whether you want to multiply and have tan over tan, or you are going to divide tan into itself 1, tan into another tan 1. Then you are left with 1 divided by 1. The result will give you a 1. This is what we mean by simplifying a trig expression, playing around with identities that we know. We know tan x, when broken down, it can also be written as sine x divided by cos x. Okay, let's move on to the next question, number 2. Our number 2 says tan squared x multiplied by 1 minus sine squared x. The moment I see 1 minus sine squared x, I think of the square identity. Cos squared x plus sine squared x equals to 1 is a special equation. And the moment I write down that, I'm thinking of the 3 versions of that identity, which can also be written as cos squared x is equivalent to 1 minus sine squared x. I have options here. If I want to, where I see 1 minus sine squared x, I'll replace 1 minus sine squared x and put cos squared x because you are equal. Then I proceed and say tan squared x for now. I want to tamper with that, times cos squared x. This is what we mean by substituting with an equivalent form of it. The equivalent form for 1 minus sine squared x is cos squared x. So where we see cos squared x, we can put 1 minus sine squared x. Where we see 1 minus sine squared x, we can put cos squared x. Depending on this question, here we are simplifying, so I would rather write it as simple as possible and write it as cos squared x. Yes. Then what do you further notice here? It's like you are stuck at that stage, but at least you have obtained a mark for correctly replacing 1 minus sine squared x. That is your trigonometric substitution using its equivalent. Yes, you will appear to be stuck, but don't forget the quotient identity. It does not only work if it's tan x. Even when you square these, the identity will still hold. What does that mean? It means our tan squared x is the same as sine squared x divided by cos squared x. What you do on one side should be done on the other side of your expression. So in this case, it's an equation. I've decided to square the left-hand side. I must also square the right-hand side. But squaring the right-hand side will demand me to square both the numerator and the denominator separately in this case. So when I come here where I see tan squared, I'll replace and say sine squared x divided by cos squared x multiplied by cos squared x. This is the same as saying over 1 if you had to create a fraction. Then you can see these can cross divide. There you go. What's left is sine squared x over 1, which still gives us sine squared x. You find some of you still having 1 over sine squared. You must know which number divides the other. Sine squared is a numerator, 1 is a denominator. 1 times 1 is a 1. So 1 into any number is that number. 1 into any number is that number. Okay, so this is how you could have collected some marks here. You'd be awarded probably, let's check there. We're marking for you. 1 mark there for replacing that. 1 mark there for replacing that. And 1 mark for simplification. And then 1 mark for the final answer. This question can give you a maximum of 4 marks and a minimum of 3. On the other hand, those two different approaches, first mark you'll be given there, just realizing that sine x divided by cos x is tan x. Then simplification, and then your final answer. This one can carry a maximum of 3. Alternatively, realizing again here that sine x over cos x changes to tan, because you saw something, that's why this time you are changing to tan. You saw that there is another tan, maybe they will cancel each other out. Then you take that route. Simplification, when you divide, then final answer, 1 mark. So this is basically how we could have marked for you in exams. Otherwise, we're moving on to the next question. The question example 2 says, simplify the following expressions as far as possible. This takes us back again to simplification of fractions in lower grades, simplification of algebraic fractions. If you want to understand trigonometry, never divorce it or detach it from algebra and general simplification of fractions. Because you can see this is a fraction. The only difference is that it's in trigonometric form. It's not just a normal x. It's a function and an angle. And this x that you see here represents a particular angle on our revolution 360 degrees or beyond a revolution. These are angles that you see here. You will never use these ratios without mentioning an angle. So they go with angles. So for 4 marks, you are expected to simplify sine x times cos x. For now, I don't see what to do there with that numerator, sine x times cos x. I would rather keep it like that and hunt for things that I know. I know the square identities. I already see some squares here, but unfortunately, if I hide this part, I don't see a plus. If I hide this part, there is a plus. So it means I can't create a 1 from cos squared minus sine squared. That identity works if it's a plus. And that sign is a negative. So it won't yield a 1 directly from there. So the question is, how do I approach this one? Let's have a look at that. Okay. What I'm noticing here is that if I say sine x times cos x divide, I will stop there and try to collect things that I know will help me. I see there is a 1 minus sine squared x. I'm going to collect these two and make them 1 like that. And then add my cos squared x. I've swapped the positions now. Remember, you are not lifting across, you are just moving positions. This is not an equation. So if it was minus sine squared, it will still be minus sine squared. Why am I collecting 1 together with minus negative sine squared x? Is because I am remembering the square identity. Cos squared theta plus sine squared theta is equals to 1. It will also work again if it's cos squared x plus sine squared x equals to 1. It doesn't matter. Even if it's alpha, it will still be 1. Even if it's beta, it will still be 1. Even if it's gamma, it will still be 1. Even if it's lambda, it will still be 1. Any angle that you put there, the answer will always be 1 in that square identity. Then I know if I make cos squared the subject of the formula, I get 1 minus sine squared x, which is what I have in my question. So where I see 1 minus sine squared x, I'll replace and put sine x times cos x divide by cos squared x. I'm replacing that 1 minus sine squared and put its equivalent form, which is cos squared x multiplied by cos squared x. This will then be equals to sine of x times cos of x divide by 2 cos squared x. This is just like in algebra. When you say x plus x, you get 2x. We are adding quantities of the same. Oh, sorry. This is cos. Oh, yes, it was a plus here. Yes, correct that. This was a plus. Right, just like in algebra, when you say cos squared, x plus x, you get 2x. Y plus y, you get 2y. In trigonometry, when we have cos squared x added to another cos squared x, we are getting 2 cos squared x. That 2 becomes a coefficient. Then you'll realize that there is a common factor here. There are 2 ways of doing it. It's either you factor out cos or you simplify. So I'll use whichever is appropriate for me. I'm going to divide this there 1. Cos squared x divided by cos, 1 cos will go. Then you cancel that 2. You remain with 1 at the bottom. So it means you now have 2 sine, okay, it's not 2 is at the bottom, is sine x divided by 2 cos x. 1 cos has been eliminated through simplification. We know the coefficient of the numerator is 1. So this is the same as saying half of tan x. Remember, sine divided by cosine is equals to tan. 1 over 2 is just a coefficient half. So this 1 over 2 or 1 divided by 2 will form a new coefficient. Then sine x over cos x is an identity. It goes to tan x. So our final answer is half tan x. Allow me to go back here. Another learner, when they get here, they can say, I see cosine is common. They will say cos. They will factor out cos here, right? They will say cos x into sine x. That's your numerator. Then here they will factor out 1 cos x into twice cos x. Remember, those coses were 2. Then you divide these, they go. This could have been simpler for you. You realize there is cos in the numerator, pull it out. There is cos squared in the denominator. You also pull it out. I think I eliminated your 2 there. Right. Then from there, you are left with sine x divided by 2 cos x. Then this will follow. That will follow because the coefficient here is 1. Okay, this is how you could have done that question using one particular approach. Let's have a look and see if you could have done the same question using another approach. I just wanted to add a page for you. Unfortunately, I can't. I wanted to have a look at how we could have also done the same. Let's see here, it won't work. It's fine. Let's just proceed. Alternatively, you could have replaced either cos squared x using your square identity equivalent, or you replace this. There are many ways in which you could have done that question by playing around with your square identities. Where you see cos squared x, you put 1 minus sine squared x, but it will eventually simplify back to the same half tan x. Otherwise, let's move on to the next question. Our next question is November 2015. This is a past exam question. It says, determine the value of the following expression. 2 sine x, it was number 5.2 in that year. It carried 4 marks. 2 sine x times cos x multiplied by 1 plus tan squared x divided by tan x. How would we simplify this type of a question? Right, let's have a look and see. We are going to maintain our 2. Let me reduce the pen. Take a thinner one. Right, 2 sine x. I prefer red. Let's choose red. Okay. 2 sine x multiplied by cos x into 1 plus, if I were you, I would break this tan squared so long and get sine squared x divided by cos squared x to avoid delaying the process. Divided by, you come to this side, is sine x divided by cos x. This will allow you to simplify. So remember, when you are dividing, you can as well multiply by the reciprocal. So we have this 2 sine x cos x into 1 plus sine squared x divided by cos squared x, all divided by sine x over cos x. You are dividing by tan. So you need to simplify now. How do we handle this one? We are going to take our denominator and invert it and simplify. So what are we saying? We are going to have 2 sine x times cos x into 1 plus sine squared x divided by cos squared x multiplied by, you are now going to multiply, let me put a bracket there, multiplied by cos x divided by sine x. Cos x divided by sine x, tip and times. Your denominator was sine x over cos x. You now multiply by cos x over sine x. You will find that sine divides with sine, they go. So what's left now is 2. You are now left with 2 cos x times another cos x, which is this one, and then into 1 plus sine squared x over cos squared x, like that. Then this gives us 2 cos squared x into 1 plus sine squared x divided by cos squared x. Then we are going to use the distributive property. I'm going to leave my 2 outside and distribute cos squared. I have a reason why I'm leaving 2. So this will then become 2 into cos squared x plus cos squared x times sine squared x over cos squared x. You are distributing your cos squared, but there is still a 2 outside. That's why I'm still maintaining a bracket. Then as this cos squared jumps in, these will divide and go. And what is left is now twice cos squared x added to sine squared x, then I close. But you will remember, this is a square identity. Cos squared x plus sine squared x is always equals to 1. So this is our 1. We replace and put 1. Then our final answer is a numerical value 2. That's why the question is saying determine the value of the following expression. It didn't say simplify, because they know eventually this will become a numerical number or value. Hence, determine the value of this. So as you substitute and simplify, at the end of it all other things will disappear. Then you'll be left with your numerical value. That's how you could have done that question there. Right. Let's have a look at how it was marked in that year. Step number 1, they converted tan to sine over cosine. 1 mark for that. We're marking for you 1 mark for this. Then next mark, identities, identifying. You'll realize what they did here, they tip and times, but in their case, they changed 1. This is another approach. Fortunately, us is another approach. They converted 1 to cos squared x plus sine squared x, which is still fine. Then that's your 1. And then multiplying by 2 sine x cos x times the other side. They have put everything under the same denominator. Then from there, you'll realize that cos squared x plus sine squared x over cos squared x, the numerator will go back to our 1. Then we simplify this device with that, they cancel and go. Then the final answer becomes a 2. Yes, that's how you could have. So 1 mark for using those identities, and then 1 mark for simplification, and then 1 mark for that 2. That's how you could have done that particular question. Then we're moving on to the next part where we are saying prove the following identities. Sin x plus cos x divided by 1 plus tan x equals to cos x. How do we prove an identity? Remember, we said earlier on, in an identity, the left-hand side is the same as the right-hand side. So the fundamental principle of proving an identity in mathematics is to choose one side and show that it will reduce and become the other side. So there are 3 ways of proving an identity, but we are going to stick to one. Which are the 3 ways? You can choose the left-hand side and show that it becomes the right-hand side. Or choose the right-hand side and show that it becomes the left-hand side. Or work with both sides at the same time, which might take longer, but at the end of the day, you must level the ground and make sure what you see on the left-hand side is exactly the same with what you see on the right-hand side. So in this case, the easiest way of proving an identity is to choose a side. Step number 1, you choose a side that you think you can simplify further. Like in this case, I can't choose the right-hand side. It's only cos. How will I play around with cos to involve sine and tan? It will be a bit difficult. So I would rather choose the left-hand side and reduce it until it yields cos x, which is my right-hand side. So let's have a look at that question. Playing around with our identities. Step number 1. That's step 1. What do? You choose a side. I'm choosing the left-hand side. So Having chosen my left-hand side, I'm going to rewrite it as sine x plus cos x divided by 1 plus, I stop there, I break down tan into sine x divided by cos x. Already I will get a mark for doing that because I know the identity that I'm using. I've broken down tan x into sine x divided by cosine of x. Then I realize that these are fractions. I'll still continue and say, okay, if these are fractions, our sine of x, if you think you are going to have a problem with so many fractions, you can so long use a different approach. Sine x plus cos x divided by, I want to combine my denominator by using a common denominator. This is over 1. My common denominator here is going to be 1 times cos, which is cos of x, the lower denominator of the denominators. Right. So 1 times cos is cos x is going to be our new denominator. We leave sine x plus cos x as is for now, then focus on the denominator. Then, since you are saying 1 times cos is x, then you divide. How many times does 1 go into cos? It's cos times. Times 1, you get cos x. Some people use what we call the butterfly method when they get there. As long as you got the denominator via multiplication, 1 times cos is cos. From there you can use the butterfly, but must be careful with that butterfly method of yours. You must take the lower denominator, which is cos, multiply by the top 1, then it will give you cos x. Added to, then 1 times sine is sine x. Then so far what we have sine x added to cos x, that's your numerator, I'll put it in brackets, divided by cos of x added to sine of x, that is your lower denominator, over cos of x. Then tip and times, this is sine of x added to cos of x, which was your original numerator, multiplied by cos of x, the reciprocal or inverse of that, divided by cos of x plus sine of x as your new denominator now. You will realize that these two are the same because of the commutative property. Cos x plus sine x is the same as sine x plus cos x. They divide and go. What's left is cos x, which is equals to the right hand side. Proven. So our right hand side is equals to our left hand side because our left hand side has simplified to cos x, which is the same as the right hand side. Then we move on to the next question. Our next question says cos x minus cos cubed dx divided by cos x minus cos x times sine squared x. This is a question that will require you to use factorization. That's why we said you can't divorce this from algebra. So we choose the left-hand side. You must always choose a side. Then I realize on the left-hand side there is a common factor in the numerator. That common factor is cos. So I'm going to say cos x, then open brackets. As cos x jumps out, you divide. Cos x divided by cos x, you get a 1, minus cos cubed dx divided by cos x. This means cos cubed dx divided by cos of x. I want to see what will remain in the bracket. The bases are the same. I subtract the exponents. 3 minus 1 is a 2. So this goes to cos squared x because 1 cos has been factored out. So for the numerator, in the bracket, I have cos squared x. Then I divide. For my denominator, I see cos is common still. I factor out cos x. Then I divide cos x into itself, 1. Then cos x into cos times sine squared x. This means cos x times sine, that's your side working, sine squared x, divide by what you factored out, which is cos x. These will divide and go. What's left is sine squared. So it's sine squared x. Right. These will divide and go. Right. You stop there and look at your remaining parts. This is very interesting because they come from square identities. This is your three variations of the square identity. Where I see 1 minus cos squared x, I can write sine squared x. By now, you should be in a position to realize that. Where I see 1 minus sine squared x, this is my cos squared x. Since the angle is the same, the powers are the same, that is the exponents are the same, and the sine divided by cosine will always yield tan, provided the angles are the same, provided the powers or exponents are the same. So therefore, this will then simplify to tangent squared x. This is tan squared x, tan squared x, which is equals to your right hand side. Your left hand side is equals to your right hand side. Why? Because your left hand side has simplified to your tan squared x, which is what is on the right hand side. This is what proving an identity is all about. There are many identities in trigonometry. This is another identity, but there are those that are called the special identities, like the two that we derived today, which is cos squared theta plus sine squared theta will always give you a 1. Then tan theta is always sine theta divided by cos theta. But there are many other identities along the way wherein if you simplify, the two sides will always balance. It means there are also identities of some kind, although we don't call them special, because those ones we derived them straight from the Cartesian plane based on our trig ratios. Okay. Then we come to this other identity. It says prove the identity 1 over cos theta minus cos theta divided by 1 plus sine of theta is the same as tan of theta. Okay. This is a very interesting one. I don't see. Where do we start on this one? Let's think. Tell me, where must I start on this one? I want to show that my left-hand side is the same as tan theta for 5 marks on the other side. And you must realize the angle is the same throughout. There is no way you can mix these angles and still call it an identity. It can only work if it's in theta, work if it's in sine, work if it's in x. The angle has to be the same. Okay, let's proceed. We are going to take our left-hand side. It seems to have a lot of things to do there. Otherwise, I can't start from tan theta. It will be a bit difficult. I realize that these are just but fractions. Every time I get fractions of this nature, I have to find a common denominator, which may not always be the lowest. But the easiest way of finding a common denominator is to find the product of the two denominators, which in this case is going to be cos theta times 1 plus sine theta. Multiplying those two will give you your denominator. It's just like saying in simple numbers 1 over 5 minus 1 over 7. If you want to find a common denominator without using multiples, you just multiply 5 times 7, you get your 35. Then you cross multiply 7 times 1 minus 5 times 1. Then this will give you 7 minus 5 over 35. Then your final answer will be 2 over 35. We are using the same idea here. We are multiplying our denominators. Cos theta times 1 plus sine theta is going to form a new denominator. I will keep it like this for now and wait for things to happen, then simplify further. Right, let's proceed. Here I'm going to cross multiply. It's going to be 1 times 1 plus sine theta, you always start with that diagonal, minus cos theta times cos theta. When you use this approach, you just multiply this diagonal times the other diagonal. You always start with 1 plus sine theta times 1 minus 1 cos theta times cos theta. Then you simplify. You proceed. What we have? We have 1 plus sine theta for the numerator minus cos squared theta divide by cos theta times 1 plus sine theta. Okay. Cos theta divided by 1 plus sine theta. I'm going to keep my denominator still as it is and then move on and say this is equals to, I'm going to group terms here, 1 minus cos squared theta to form a sine squared theta plus sine theta divided by cos theta into 1 plus sine theta. When you get to this level, it looks like you are a bit stuck, but let's proceed. Don't forget 1 minus cos squared theta is the same as sine squared theta plus sine theta. Those are not like terms because the other one is squared. You can't add the two. Divided by cos of theta into 1 plus sine of theta. Then this will further sine of theta. Sine of theta. When you look at the numerator, there is a common factor there, is sine theta into, when you factor out, you remain with sine theta. 1 sine theta will remain in the bracket, sine theta, then plus 1 divided by cos theta into 1 plus sine theta. Then these will divide and go. They are like terms. What's left is sine theta divided by cos theta, which is your tan theta. Again, we realize that our left-hand side simplifies to tan theta. How did we do it? We first of all treated this as a single fraction by finding the common denominator. Then from there, we found our numerator through saying 1 plus sine theta times 1 minus cos theta times cos theta. Then along the way, we formed our special square identity, 1 minus cos squared theta plus sine theta. This actually is sine squared theta plus sine theta. Then we realize that sine theta is a common factor. We factor it out, then some parts divide and go. Then we'll be left with our tan theta. Right, so 1 mark for common denominator, 1 mark for this 1 minus sine squared theta. You have to pick it up there. That 1 minus cos squared theta will yield your sine squared theta. Right, but here they used a different approach. They broke this down, but at the end of the day, when you simplify, it will yield the same results. That's the interesting part of trigonometry. Once you know your identities, you can replace anything at any time. You can break down that cos squared theta into 1 minus sine squared theta, but when you open your brackets, you must be careful there. This will then change to a plus. Then simplify by factorization and then simplify further. These will divide and go. Then your final answer will be tan theta, which is your right-hand side. So this is how you could have obtained your 5 marks. Alternatively, you could have found the common denominator the same way we did it. This is the approach that we used. Otherwise, they used a different approach here, wherein instead of writing this, they broke it down to 1 minus sine squared theta equals to cos squared theta. They replaced instead cos squared theta, but at the end of the day, the results are going to be the same. Okay, that's how we could have done that question. All right, so we are going to look at our worksheet. There is your question number 1. These are the questions that must go in practice. They are worth 30 marks. That's your question number 1. Then your question number 2, you are supposed to prove the following identities. The first one is marked out of 4. The second one is marked out of 4. Third one marked out of 4. And the fifth one is marked out of 5. Once you practice all these questions, playing around with those identities, by the time you finish practicing these or going through them, making sure they balance, then you'd have amassed a lot of skill of answering these types of questions in trigonometry. Otherwise, how do we prove an identity? You start with one side, if given left-hand side and right-hand side, and you choose the most complex side. Don't choose a side that is already simplified. It will be difficult. Choose the one that still has a lot to be done on. Then apply your non-identities. Use your algebraic manipulation, that is factorization, multiplication, addition, subtraction, and division of terms. It's helpful at times to change from tan to cosine and sine. That is when you come across tan. Sometimes it helps to break that tan. Sometimes it helps to change that sine over cosine back to tan by playing around with what we call our special trig identities. And always check your work. Don't just cruise and proceed. One mistake can spoil everything. So make sure once in a while you stop and check, am I doing the right thing? Because it will be difficult if this identity doesn't come out. You'll have to go back and trace, and tracing where you made a mistake might be a bit difficult. Otherwise, you need to practice and practice and practice those questions. You'll eventually get there. So in this lesson, what did we learn? We learned how to derive our two special identities, cos squared alpha plus sine squared alpha equals to 1. And we also derived the identity tan alpha equals to sine alpha divided by cos alpha. In this case, we are saying for alpha not equals to elements of this 90 degrees, where that k is odd integers. It will never work if k odd integers are used, right? So it's a quotient. We also simplified trig expressions by using trig identities. We also proved the trig identities by using trig identities that we have derived today. You are proving other trig identities. We also had a look at trig identities as a definition that they are equalities that involve trigonometric functions and holds true for all values of the variable given in the equation for which both sides are defined, meaning there are no zero denominators. Otherwise, our session is going to end here for today, and thank you for coming. Continue practicing. You'll eventually master the skill of trigonometry. Otherwise, thank you for coming, and goodbye.